Hello there, everybody. This video is about areas in the plane. This should look familiar to you. I'll make it short and sweet. What we'd like to be able to do is find the area between two curves. Okay. Before we've done it with Riemann sums. This particular one I've drawn here is with rectangles. The width of these rectangles here we could call delta x. The height, or this other dimension of the rectangles, is actually f minus g. And over here it's a little obvious why it's f minus g. F is the distance from the curve, this top curve, all the way down to the x-axis. G of x is the distance from the second curve down to the x-axis. And if you subtract them, you get the distance from here to here. And over here it works to f is the distance from here to here, and g is negative. It's the distance from here to here, but it's negative again. So when you subtract them, it makes that negative distance positive and kind of adds it to this, giving you the total distance from here to here. In any case, the distance, that distance is f of x minus g of x. And you're going to multiply that by delta x to get the area of one of these rectangles. And we would want to add them all up in order to get an approximation. Well, and when you make these rectangles infinitesimally small in width, the delta x becomes the dx, and the integral does the same thing as the sum. And so we get the integral from a to b. We need to have bounds. We want to go from a to b of f of x minus g of x dx. That gives you the area. Let's take a look at a couple examples. Actually, one thing before we go away from that. And this works as long as the top function and the bottom function are the same. If they change, maybe they cross, or so the other one is above and the one that was on top is now below, then you've got to do some other things. You've got to tweak your method a little bit. But as long as the top function is the same and the bottom function are the same, this will work fine. Again, let's take a look at a couple examples. So this first one, got the square root of x and the line y equals x minus 2, and we want to find the shaded area. Now notice the top function for the shaded area is always the square root of x. It's fine, but the bottom function changes. From 0 to 2 it's the x-axis, and from 2 to where they cross, at 4, it's the line y equals x minus 2. So there's actually two different integrals we're going to have to find here. One to find this area to the left of the dashed line that I just drew, and another one to find the area to the right. Again, because the bottom function changed. Now I know it's pretty obvious here where these lines cross. They cross it at the point 4, 2. If you didn't know that, you would just have to, or if you didn't know it from the graph, you would just have to set these two equal to each other. Solving that equation will tell you the x-coordinate of where these lines cross. And you can, if it's easy, you can do it by hand. If it's a more complicated one, then your calculator will do it. Can do it for you as well. Okay. So here we're going to just say it's the 0.42 is where that happens. So this first integral. Now our bounds are going to be from 0 to 2. Now the top function is the square root of x, and the bottom function is just y equals 0, so we don't really need to do anything. We could put minus 0 if you wanted, but so that gives you this area. Now on the right side over here, now we've got a different bottom function. It's not the x-axis anymore, it's this line y equals x minus 2. So that's why we have to do a separate integral. We're going to add the areas together to get the total area. And we want to go from x equals 2 to x equals 4. And its top function, root x, minus bottom function, x minus 2, dx. Don't forget the dx. That is important, and you will see why tomorrow, in in the next lesson. But now we've got a couple of integrals that we can evaluate to get the area. And these aren't too bad. This one is, let's see, 2/3 x to the 3/2, evaluated from 0 to 2. And then this one, I got that again. Minus, let's see, x squared over 2 plus 2x. These signs changed because of the parentheses. And that all is evaluated from 2 to 4. And I trust that you can do that, so we can stop there and move on to the next problem. Okay, so here's another one. We've got the parabola. We've got a parabola, y equals x squared. We've got a line, y equals 1. There's kind of these three kind of part area here that we want. And notice that the top function is different. Over here, the top function is the parabola. The bottom function is y equals 1. In the middle here, the top is y equals 1. And then it changes back. Again, the top here is y equals x squared. So there's going to be a couple of different integrals that we have to set up here because the top and the bottom functions are not always the same. In fact, they switch. They switch twice. Again, if it wasn't obvious where these crossed, you could just set y equals x, or x squared, and 1 equal to each other and solve it. You get x equals plus or minus 1 in this case, and that would tell you where these lines crossed. Might not be necessary here since I drew the graph to scale and you had grid lines to look at. But if you don't, that's how you figure out where they cross. Okay, now let's set up some integrals to find this area. Okay, so this first one over here, we're going to go from -2 to -1. And the top function is x squared, and the bottom function is 1. So we're going to go x squared minus 1. Top minus bottom. Now, if we look closely here, we can actually save ourselves some work. These two areas are exactly the same because of the symmetry of a parabola. So I'm not going to have to, I could set up a separate integral for this one, but if I know this integral, I can just double it to include this one. So let's just double it. Now that takes care of both of these parts over here. Now all I've got to deal with is this. And anytime there's symmetry like that, by all means, make it easy on yourself and use that symmetry to your advantage. If you can avoid setting up extra integrals because of that symmetry, definitely go ahead and do that. So for this middle part, we're going from -1 to 1. And the top is 1. The bottom is the x squared. So 1 minus x squared dx. And there we go. Now all that's left to do is to evaluate those integrals. It's always top minus bottom. You got to separate or set up separate integrals if the top and the bottom function changes.